So we're going to find some large prime numbers. Remember, that's an important part of creating an RSA key. So Fermat.pi here is going to do it. Now, Fermat's little theorem says that any number to the p minus 1 is 1, mod p. And so we can test this condition for random values of a to see if a number is prime. Any number to a prime minus 1, mod p, will be 1. So if you use a random value of a and see if this is true for a candidate prime p, it is something that you know will be true for real prime numbers, and it's probably not true for non-prime numbers. So if you just try it for some random values of a, that's evidence that p is probably prime. And this is how you do it. So all this is going to do, I put in a potential prime, and it's going to 5 times take a random integer and raise it to the power p minus 1 mod p and see if that equals 1. And if it is, then it passes. Otherwise, it fails. So if I run this, Fermat, and I give it a potential prime of, say, 7, it passes 5 times because 7 is really prime. But if I give it a 9, then it fails every time because 9 is not prime. And this will work to test any number you want. So if I wanted to try a difficult one like 112255, say 7, I don't know if that's prime or not. I think it is not prime. But I could try others in the same area, like 112255, 9. That's also not prime. I could just keep going. 112255, 561, just counting up through the odd numbers. And those not prime either, but eventually I'll find a prime. So that's the game here. Now, you can try this. This is a large prime number, so let's try that. If I run this and put in this number that's 1024 bits long, it's prime. Pass, 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 pass. So this test is pretty good. It's not perfect, but it's pretty good. And so now you might wonder, how many guesses will it take to find a prime number? The prime number theorem says it follows of 1 over the natural logarithm of n. So you can find out, you can calculate that in Python. So this should be the density. This will just calculate that value. It will import math, and it will do math.log of n, 1 over, so it's going to tell me the density of primes. If I'm going to, it's going to take from the user what power you want to try. So if I run this, Python density, and I put in, say, 10, these will be 10-digit numbers. For 10-digit numbers, 4% of them are prime. And 100-digit numbers, 0.4% of them are prime. So 1 in every 200 about. And for 1,000-digit numbers, 0.04% of them is prime. So this is the essence of how difficult it's going to be to perform RSA. If I need numbers that are like 100 digits long or maybe 300 digits long, which is the region where you work, because remember we want to be 2,000 bits or 4,000 bits, and it's about 3 bits per digit. So a 1,000-bit prime number is about 300 digits long, and the others are maybe 600, 900 digits long. So in this range is where the numbers I'm going to be using, and there, see here I have about 0.4% primes, so I'd only have to try 200 or 300 guesses before I'd find a prime number, and down here 2,000 or 3,000 guesses before I'll find a prime number. So it's not going to be incredibly difficult to find them. All I'll have to try is at most a few thousand guesses to find a P and another few thousand to find a Q. Even though the numbers are unthinkably huge, the density of primes stays pretty large. So that means you can find prime numbers all you want to. So here's 10 to the 300 is not prime. It's the product of 10 many times. So start there and just count up until you find the first number above it, which is prime, and you'll find that flag. So it's a small modification of these programs to do that. And then the next one is to find companion primes. 11 and 13 are both primes, so they're primes as close as they can possibly be. Now, no even number larger than 2 is prime. They're all divisible by 2, so the closest 2 prime numbers can be is 2 apart. These are called companion primes. And those happen, so again, you can just start here and count up until you find the first companion primes. And because of the density of primes we just calculated, it won't take forever. You might have to try 50 or 100,000 guesses, but not more than something like that. And Python is very fast, so you can easily try tens or hundreds of thousands of guesses without having to wait very long. So that's one project I wanted to show you.